Well, hello everyone. Welcome to Open Hardware TV Season 1, Episode 4. And today's episode, we're going to be focusing on a new project in the Open Hardware Group ecosystem called the Core-5 Mcu SoC. We have a number of speakers with us today, and as we've done with previous episodes, we pre-record the content in order to improve the viewer quality. So we'll live stream that content in just a moment. We have the speakers here with us. We're going to watch the live stream together with all of the attendees. So wave hello to everyone, guys. And we'll bring the speakers back live at the end of the pre-recorded content, which is about 35 minutes or so in length. And in the meantime, as we're live streaming the content, if you have any questions, enter them in the Q&A section. We'll just queue up all the questions and then come back on live at the end, read the questions out and answer them and have a discussion. And if that generates more questions, that's even better. So with that, make sure you enter those questions in there. We'll be back at the end of the live stream. And here comes episode 4. Thanks for joining us. Okay, hello everyone. Welcome to Open Hardware TV, Season 1, Episode 4. The topic for today's episode is the Core-5 MCU project we have starting up within the Open Hardware Group. Open Hardware TV is a series of live stream video casts that describe some of the projects that we have underway within the Open Hardware Group ecosystem. And we bring a new episode to you every month. So let's jump into the agenda for today. Today's episode, like I said, is about the Core-5 MCU project that we have underway at Open Hardware Group. And I'm going to start off by providing a quick overview of the Open Hardware Group ecosystem. Then we'll bring in a panel with Brian Wisp from ARC Investments, Brian Fate from QuickLogic, Tim Sachs from QuickLogic, and our own Davide Schiavone from the Open Hardware Group, and he's our Director of Engineering for the Cores Task Group. And you might also know Davide from his work at ETH Zurich, where he's been pursuing his PhD. Following that, we'll bring Brian Faith back and Tim Sachs back from QuickLogic. They'll provide a quick overview of QuickLogic company and their motivation for being involved in a test chip with ETH Zurich called Arnold, which resulted then in the beginnings of this project and the Core-5 MCU SoC project. And then we'll switch over and bring Brian Wisp back in from ARC Investments to talk about why a private equity investment firm is involved in open source hardware development. And then we'll end the episode with an overview from Anu Gupta from Global Foundries, providing details on the 22FDX geometry node that will be producing the Core-5 MCU in. So with that, I'll jump into a quick overview of the Open Hardware Group. Open Hardware Group is a global organization driven by its members and individual contributors, where hardware and software developers come together to work on open source cores, related IP, software, and tools, such that this IP can be used confidently in high volume production SoCs. Our focus is really on producing industry quality IP, open source IP, that adopters can trust. We have developers from all over the world, in North America, in Europe, and in Asia. We've got more than 54 plus members and partners now, ranging from strong industry corporations, very, very large systems companies, semiconductor companies, tools companies, software companies, a very, very strong academic research part of the ecosystem, with institutions from around the world doing research using Core-5 and Open Hardware Group artifacts. And then we're also supported with a very strong partner community that's helping us bring these open source IP blocks to the ecosystem. So what got us all started was a couple of projects that were contributed out of ETH Zurich under the Pulp Platform project under Luca Benini's guidance and leadership. In particular, the Risky Core and the Ariane Core. The Risky Core is what we call the CD E4, an embedded class 4-stage core in the family. And the Ariane core, which we call CVA6, is an application class 6-stage core that is available in either 32 or 64-bit mode. And together, these cores are the first two cores in our family of open source RISC-V processors, which we call the Core-5 family. As I said at the outset, this is episode 4 of Open Hardware TV. If you missed the first episodes, they're available for playback on our site. You can navigate to openhardwaregroup.org, click on the Open Hardware TV menu, and download or stream the episodes from episode 1, 2, and 3. In episode 1, we covered the verification test bench that we use to produce industry quality IP. Episode 2 covers the actual cores themselves. Episode 3 covers the hardware and software task groups within Open Hardware Group that are working on board level and tool chain projects in support of implementing those cores. So I'd like to bring in Brian Wisk from ARC Investments, Brian Faith and Tim Sachs from QuickLogic, and Davide Schiavone from the Open Hardware Group. Gentlemen, welcome to the episode.
Hi, Rick.
Great to be here.
Thanks, Rick. Great to be here.
So let's start maybe, Davide, with you, and you can maybe tell us a little bit about the Arnold test chip that was part of your research at ETH Zurich and the motivations behind that research project.
Yes, the Arnold test chip is a joint project between ETH Zurich and QuickLogic, and it's basically a microcontroller based on the Palpissimo open source platform, where we are integrating the QuickLogic Efpga to explore different way of reconfigurable accelerators. So it's in the edge computing devices, it's very important to have accelerators to push beyond the current limit, the energy efficiency, and Efpga is a way of doing that. We did it with a joint project between the two. We actually implemented this Arnold chip here that you can see on my back in Global Foundries 22 nanometers technologies.
Excellent. Okay. So maybe we'll bring in Brian Faith and Tim from QuickLogic and maybe guys give us an overview of what your motivation was for participating in this research project.
Yeah, I can start, Rick. We've been doing low power computing in the edge and endpoint for a long time, but it's been with ARM-based processors, microcontrollers. And we started an IP licensing initiative a few years ago. One of the first nodes that we ported to was 22FDX at Global Foundries. And lo and behold, we ended up at the trade show in Munich, where we met Frank, who works with Davide on this program at ETH in Zurich. We started talking about, we understand use cases for embedded FPGA, but we don't think the whole world does. How can we put more proofs out there, more platforms for research to have papers that actually can inspire more use of this in the future? That spun off a series of discussions that they were looking for exactly a 22FDX version of their chips, which is behind Davide there. And it was just a great engagement. So we basically contributed the eFPGA core. We worked with them on how to stitch it in for the right architecture. And at the end of the day, there's a great chip, really low power, showcased embedded FPGA use cases. There's a great research paper now available. And so this is sort of the starting point for us to actually take what we've leveraged with the ARM-based processor microcontroller over into the RISC-V domain. So we're really excited with the engagement, incredibly sharp guys at ETH in Zurich, and I think the proof is in that research paper.
Cool.
Thank you.
Tim, can you comment on why 22FDX? What attracts you guys to that node? We'll hear from Global Foundries later in the episode, but I'm curious from a user standpoint, what attracted you guys to that node?
So there are a couple of aspects to it. So we care about energy efficiency, and we also care about economic efficiency because we want to be shooting for IoT kind of applications where people need relatively low cost parts. So 22FDX, it's an SOI-based technology. So that means that you have the option of dynamically switching between performance and power savings. So you can just imagine that's very useful in this environment. And it has an excellent energy efficiency. So that was good for us. And that particular node, Global chose it because it's the smallest kind of features you can do with double patterning. So what that means is it's the cheapest per square millimeter node that you can hit. If you go smaller, then your cost jacks up because you got to go to triple patterning. So it seems like a very good place for IoT kind of devices.
Interesting. Okay, Brian Wisk, we'll transition to you now. And this so far, what we're talking about here today is, turning that research project into a production quality SoC, and leveraging that open source development. You're kind of the different character in this panel from the investment community with ARK Investments, a private equity investor. What's motivating you to invest in open source hardware development?
For us, it's really a simple bet on edge IoT being a power game and a mass customization game. So the only, why everybody's going from an investment standpoint, you can look at the NVIDIA deal with ARM as the most recent example towards, deeper and deeper domain expertise. We're sort of taking the opposite approach where all the innovation is going to happen in a shallow, very quick end-to-end turnaround for an SoC. And I think where that game is won is in the ultra low power setting. So I think my first exposure to this was the work that was done out of ETH with Arnold, and just some of the impressive results with a very, I think novel approach to how to get that acceleration and that customization that we were looking for.
Cool. So that's interesting. I want to be a little controversial here, and throw this out to Brian and Tim. All of those statements are true, but why open source? Why not just invest privately, build proprietary platforms, and push the product out in the marketplace? Why is open source hardware IP development attractive to you guys?
I think I can start for QuickLogic. This was a journey that took us around a year, talking with different folks in the community to come to this conclusion that by going with the open source route, not just hardware, but also the tooling on top of that, it actually opens up so many new users that today don't have rural access to hardware. The more you can make hardware look like software, you open up to this sort of 10x number of users. You want to make it easy to use and abstract the details of the hardware with software. And I think there's just an incredible amount of innovation happening in the open source domain that Tim and I didn't fully appreciate until we went to the OR conference in Bordeaux about a year ago. And that really just hit us right across the face that there's a lot of tools, there's a lot of IP there that are of production quality. And now is the time to really jump into that so that we can participate.
And I think from my perspective, one of the things you have to understand is that we spend a lot of energy building our IP. We have engineers that worry about the application. So I have DSP engineers and those kind of people, domain experts, but we can't cover all the domains. There's just too many domains out there. So we look at this and we say we have this huge investment in this eFPGA that can address a wide variety of domains. We can't hit all of those domains. We can't build examples for all those domains. We can't excite people about all those domains. So by opening this up, we can access a community of people who we've never even thought about, who say, oh, I could use an eFPGA to do this or that or the other thing. I think that's what's exciting about this. This ties into that mass customization rather than one particular domain.
Cool. Brian Wisk, anything to add to that?
Yeah, just extending on what Tim said, it's really about if you're going to be able to ingest that many, different domains that maybe, have a very specific use case where the end market is much, much smaller. The world we live in today, when you're investing in new IP, you have to think about, end markets in the billions per chip and all of the upfront CapEx that goes into that, sort of everybody's funnel has over the last 30 years funneled to that construct. I think what IoT and really what people don't understand about Internet of Things today is the ability to do a lot of the computation at the edge versus feeding data into the data centers and doing computation there. So that explodes the number of sort of multidisciplinary tasks that you have to do, which means you really need to bring the upfront CapEx down to below 100 million to think about, new IP, and even lower than that. So I think with Arnold 2.0, our first goal is, could we do something that's, commercial ready under, 20 million in upfront investment? And I think this is going to be an exciting first attempt at that.
I couldn't agree with you guys more. So thanks for the discussion here. Stay with us because we're going to have a viewer Q&A at the end of the session, and we'll move on to some of the other talks now. Thanks, guys.
Thank you.
Thank you.
Thank you.
Now we'll bring in Brian Faith and Tim Sachs again, but this time to give us an overview of the QuickLogic Corporation and their motivation for being involved in the research project with ETH around the Arnold test chip, as well as how that leads into our production quality Core-5 MCU project. Welcome to the episode. Welcome back to the episode, Brian and Tim.
Thanks, Rick. Let me give you folks a brief overview of QuickLogic. We have three primary product lines. We have a semiconductor IP product called Embedded Fpga that's useful for this project. We have a very low power line of SoCs, or microcontrollers, that are focused on edge and endpoint applications. And we have an AI software platform company called Sensimal that we acquired about 1.5 years as a spinoff of Intel. These three product lines comprise this platform offering that we have available today. What we announced earlier this year was an open reconfigurable computing initiative called CORE. And through a collaboration, a deep collaboration, in fact, with Google and Antmicro, we have now contributed some of the architecture information on our embedded FPGA and our microcontrollers so that they can be very well supported in the existing open source tool chains commonly used today in embedded systems. The FPGA tooling, of course, being SymbiFlow, shown here, Renode for system emulation, and other tools that related to the microcontroller development. So all of these are very germane for the discussion today, related to how this can translate over into the future based on an Arnold or a Core-5 MCU. And at that point, I'll kick it over to my colleague, Tim.
Hi, thank you, Brian. So the Open Hardware Group has a big, hairy, audacious goal, which is to build production-ready cores. The reason for doing this is that engineers are skeptical. As you heard in the panel discussion, Brian said that we weren't sure open source would work. We're sure very many other customers are the same way. And in fact, what you see is a progression of open source people not believing in it, then they start to believe in it, and now the buzz is, oh, it's not verified very well. And we know that what will happen after verification is they'll say, well, we actually need to use it before we believe in it. So building this core is a way to do that. QuickLogic went through the same process. ETH Zurich core that Davida talked about was an academic version, and that was our way of getting convinced of this. The diagram of the core shows that the eFPGA in the middle, not because it's the most important part, but because it connects to every other part of the system. So use cases are multiple. One use case is data streaming in from the peripherals to the UDMA, getting processed by the eFPGA and then presented to the RISC core. Another use case is in reverse direction, data going from the RISC core through the eFPGA, micro DMA out to the peripherals. And then the third case that everybody talks about is an accelerator, where the RISC core prepares data in the memory, and then the tightly coupled data memory with its large bandwidth is accessed by the eFPGA. The eFPGA munches that and pushes the data back into the memory. Arnold, as described by Davida, is a heterogeneous energy-efficient architecture. It is a RISC-V general-purpose processor. The one we used in Arnold was the predecessor to the one the Open Hardware Group's working on. It has 512 kilobytes of onboard memory, and it has a peripheral set that's compatible with IoT, which is different than what you'd see in an application level processor. The benefits of this are an energy-efficient architecture that gives you flexibility to implement hardware partitioning of software requirements, lower unit cost than discrete MCU versus plus discrete FPGA implementations. So the idea here is that you could use a discrete application, but for IoT, you want to merge them into one chip to get the benefits of semiconductor economics. OTA hardware upgrades. Well, ASICs are always the lowest power, most energy efficient way of solving any problem. But once you built them, they're stuck. So with eFPGA, you have the option of upgrading the hardware over the internet after it's deployed in the field. And of course, you get lower NRE costs versus spinning an ASIC for each derivative. System partitioning in low power computing, software is the go-to method everybody uses. It's the most flexible method to implement any function. However, it may not fit in the process available compute capability, especially in a resource-limited environment like IoT. It might not fit in the process available memory footprint, might not be able to keep up with the required AI inferencing rate within power budget. So there's two sides to performance. One side is how much performance can you get at a given power budget, and the other side is just how much performance can you get, period. And it may not be able to implement strict I/O timing requirements. So this is the place where onboard eFPGA is an ideal implementation vehicle. I'll give you two eFPGA use cases. One is hardware offload accelerated DSP. So DSP functions, filters, are an integral part of very many edge applications such as audio processing for voice recognition, although they can be used for other kind of inputs from various sources. So in lieu of running all of the DSP functions software on a general purpose processor, what you can do is offload some of them to the eFPGA with its tightly coupled digital signal processing blocks. So data comes in, say from a microphone, gets filtered, and then fed to the RISC-V processor. So the benefit is more computational capability, so the RISC-V processor is left free to do other things like the voice processing or accessing the internet or whatever else has to be done. The other use case is hardware offload accelerated AI. So here we've been looking at, for instance, AI using TensorFlow. So we took one of their visual wake word applications, which is visual inferencing application. We've ported part of the process into the eFPGA. So we take the things that are done very many times and put them in the eFPGA, and the things that are done only once are left in the RISC processor. By doing that, we can achieve something like either 5 times more performance out of the unit than we could out of the RISC-V on its own, or we can achieve the same performance at 1/5 the power, both of which could be very valuable in the IoT application space. So the project we've kicked off with the Open Hardware Group is the Core-V MCU SoC. The audacious part of it is the tape out in early Q1 2021. The project was announced at the Open Source Developer Forum. We're shooting for a real-time operating system capable 600 megahertz CD32 MCU host CPU, the embedded FPGA for playing with these 6 hardware accelerators and demonstrating the other functions you can do with the FPGA. There are multiple low-power peripheral interfaces. These are like SPI and GPIO, which are very suitable to IoT applications for interfacing with sensors, displays, and connectivity modules. And of course, you can use the eFPGA also to directly interface to different sensors that will require different interfaces. And it will all be built on 22FDX at Global Foundries for the high energy efficiency that process brings.
Great, thanks very much and appreciate your support. Please stay with us for the Q&A portion at the end of the episode. Okay, so for our next session, I want to bring in Brian Wisk from ARK Investments. And Brian, it's interesting, we have 54 member companies in the Open Hardware Group, ranging from academic research institutions to very large systems companies, to chip companies, IP companies, software developers. We have one private equity investment firm in ARK Investments. What are you guys doing here?
That's a great question. I think that if you look at the way the world is going as far as capitalizing, large scale investments, so we'll call it hardware as a service. I mean, there's different ways of looking at it, but the world is moving towards models like AWS, where large asset bases are being pooled and centralized, and then companies build on top of that or rent or lease, almost like a utility model, but it's a private utility, not a public utility. So we're very interested in investing in models like that, and that's what we do. The downside of that is you can't make a priori assumptions about which technologies are going to win out over the next 10 years. So going all the way down into the silicon is a way of, and from an open source hardware standpoint, that's where we see, where the next generation of multi-billion-dollar and hopefully someday trillion-dollar semiconductors companies are going to come out of, by, just like in the software world, building on top of a common layer or open source layer of commoditized tech.
Okay, so part of the way that we see the Open Hardware Group being structured is to ensure that these open source IP artifacts are adopted and commercialized. The software industry, has been successful with open source software development because, in fact, there's been a path to commercialization. So how are you guys structured to have that make sense from an investment standpoint?
Sure. I mean, it's not rocket science. I mean, the way you reduce risk is like everything else. You take as small bites as possible. So in this slide that I'm presenting here, all of the technology investments or IPs that we allocate capital to are sort of grouped into buckets. And then when we put call it 50 to 100 of those together, it really don't need that many to succeed in order for you to lower your risk. So it's a pull finance method where each of these verticals where we deploy those technologies, again, this is all in the context of edge IoT and wireless sensor networks, are going to rely on some winner that comes out of these pools. So if we can accelerate the rate that we're innovating, and that's the whole bet on open hardware, we can really reduce the amount of upfront capital or capex that we need to deploy to make this happen. Where that really comes to play is not just in risk but in time. So if in each of these bets in the asset companies, whether it's the wearables market in healthcare or electric vehicles and autonomous vehicles and transport that are sort of real ground zero for all of the competition in the semiconductor space, we find that if we can reduce the end-to-end time of innovation, we can improve our overall risk-adjusted returns for these pools of capital. And so that's the goal. Open Hardware Group and Arnold 2.0 would fit into one of these, smaller blue boxes down here at the lower right-hand aspect of the slide. And hopefully, this is just the first core, RISC-V core that we get behind, and then over time, this becomes a standard that other people buy into as well from a commercialization standpoint.
Okay, very, very interesting. Thanks for that insight. And stay with us because we're going to have viewer Q&A at the end of the session, and I'm sure there might be some more questions for you. Thanks, Brian.
Thanks, Rick.
Okay, now we're going to bring in Anu Gupta from Global Foundries to talk about the 22FDX node. Welcome to the episode, Anu.
Thanks, Rick, for giving me the opportunity to present 22FDX. Before we present 22FDX, I want to actually give a quick overview of Global Foundries. We are the world leading specialty foundry, approximately $6 billion in revenue. In terms of the global footprint, we have pretty much like 16,000 employees worldwide, more than 250 clients, means this is, I think, a little dated. In terms of the manufacturing capacity, we are you can estimate approximately 3 million wafers per year of 300 millimeter equivalent of wafer capacity. One of the things which we take a big pride is in that we are pretty much in every possible smartphone that you see in the world today in terms of the RF chips. So that sort of gives you an idea that we pretty much works with every possible semiconductor manufacturer in the world. So let me give a quick overview of 22. Like what is really 22FDX? When we talk of 22FDX, one of the things which always comes up in discussion is 22 bulk. And those are two different beasts basically. 22FD SOI is, as the name suggests, is fully depleted SOI. So first thing is the SOI. So obviously you have lower parasitics, that's what you expect from SOI. But even beyond that, when you say fully depleted, that gives a huge advantage in terms of the technology. Okay, what does that mean? It is a it basically reverses the short channel effects in short or basically sub 28 nanometer. So that is one very important aspect of it. As we go lower and lower channel length, one of the biggest challenges that comes is leakage increases. Okay, and that leakage increases because of dibble. And so effectively, what this particular technology node gives is that it reduces that effect, and because of thin channel. Second aspect is the thin buried oxide. So what that thin buried oxide gives is it actually gives you advantage of tuning the threshold voltage. So effectively now, instead of having to work with high supply voltages, you can actually go for different application, different frequencies requirement. You can actually go all the way to 0.4 volts. So that is what it brings to the table. Not just that, but depending on your application in the mode where you are, dynamic or in the standby mode, you can actually have the advantage now of dynamically changing the threshold voltage to actually go higher speed or reduce the leakage when you're in standby. So overall, there's a lot of different benefits that we have of 22FDX. I cannot cover all of them, but I did include a link to the 22FDX product brief in this slide. Okay, so another thing which I want to highlight is the overview in terms of the features that it brings to the table and what we enable in the technology. So first thing is power efficient digital. So that is no brainer, as we talked in the previous slide. You can go all the way to 0.4 volts in terms of dynamic voltage. You have a very low leakage SRAM, something that you probably not seen any of the bulk CMOS or even in the FinFET side of thing, which is sub 1 picoamp per bit cell. Very high area efficiency in terms of the gate per millimeter square. And last but not the least, we have enabled, instead of flash in this technology, you see the NVM option as EMRAM, which gives you a huge advantage in terms of the write power. Okay, because in the flash you need high voltage for writing, and that creates both. It takes longer time, and it also takes much more power versus the EMRAM. So that's a big advantage that you see for any of the emerging edge IoT application. Second, another component which is very important to highlight here is it's absolutely perfect for RF, analog, and millimeter wave applications. It has a very high FT and Fmax, and you can get more detail from the product brief that we have put in there. Second aspect is you can integrate pretty much the complete RF front end, including the switches in the process node for your IoT application. That gives a huge advantage in the bill of material. Another aspect is you can actually integrate the PMIC and battery management for low power application, as well as for where you have concerns of the parasitics coming off, board parasitics that comes in place and for high power application as well. So another advantage that you get in here without any additional cost, you actually have those LDMOS devices on chip. And last but not the least, the very important part of this FDSOI process node is that you can actually have a much low noise and mismatch because of no doping or dopant fluctuation in there. So you have we do have non-dope channel, and that sort of gives the advantage in terms of noise and mismatch, and short channel effects is anywhere lower. So now you can actually design with pretty much lowest length devices for the analog high performances circuits as well. And that sort of gives you advantage in die area and power, both. Last, in terms of the IPs, if you look in there, we definitely enable UL and ULP libraries for different voltage domains. We have the whole slew of body bias enabling for both static and adaptive body bias, whole slew of memories. Because we see this technology has a huge advantage in terms of the RF and millimeter wave, we have enabled the connectivity and security IPs in there. And last but not the least, this technology is Order G1 qualified already and ideally suited for millimeter wave and 5G radar application. And we have both enabled the technology and the IPs for automotive qualification. Okay, so that completes my overview of 22. And one of the things which I want to highlight as I leave here is that this is absolutely perfect technology for Core-5 MCU development. Not just today, but even for the future generation, because this gives you enough juice in the technology as of now to not just develop for today's MCU, but also for edge IoT applications going forward, where you see more and more of AI coming in picture. So overall, what I would say is this is a perfect process node for Core5 MCU. And just because of all these different properties, it's great that if you build on top of not just today MCUs, but going forward in future as well on the FDX node.
All right, now it's time to switch over to the live Q&A with our attendees. So keep your questions coming and we'll read them out and answer them live here now. Thanks very much. We'll bring in the speakers who were just on the session. Unfortunately, the team at Global Foundries actually has a large event that they've scheduled on their own today. So Anub won't be joining us, but well, we can take a stab at answering any of the 22 FDX questions that might pop up. So if you haven't done so already, please type your questions into the Q&A chat box. We have a number of them there already. So what we typically do in past episodes is we'll read out some of the questions. There's a few of them that are similar and overlap, so we'll try to group the topics together. I'll read them out, and then we'll ask our speakers to just sort of chime in on the answers. So there's been a question, several questions actually entered in around the verification methodology. So Tim kind of touched on the naysayers or the barriers that people look at. First of all is like, okay, is this stuff really real, and okay, is it any good? So the verification methodology that we use and our system Verilog UVM test bench, I'll make a couple of comments on just the philosophy behind our verification approach, and also encourage you viewers to go back to episode 1 where we covered the test bench in detail. And in fact, coming up in October, our next episode, we'll be talking about basically RTL done, right? A free RTL freeze milestone where we're finished with the verification approach at the RTL level. But that'll be episode 5. So our approach all along has been leveraging existing commercial tool flows, system Verilog, UVM-based simulators that the big semiconductor companies use, and that's generally the big 3 CAD guys, as well as for us, we use DSIM from Metrics in the cloud as our sign-off simulator. But all of the work that we're doing is around leveraging commercial tool flows, and primarily, as we've talked about a few times, that's because we want to make it easy for large commercial organizations to adopt these IP blocks and have confidence in them. And the best way to do that is to make it such that they drop right into their existing tool flow and methodology. There's a lot of good work going on in open EDA space, in the industry overall. That's not what we're focused on. And I don't know, Davide or Tim Sachs, if you want to comment on the approach that Open Hardware Group has taken around verification for the viewers. You're on mute still, Davide, I think. There we go.
Hello, everybody. Here is Davide. I can comment about the Core5 IP that we are verifying, as has been said during the episode 1. So the main component of this MCU is the Core5 CV32E4 IP, and this is actually tested in its own test bench in an ad hoc environment with a random test generation, comparison against a reference model, interrupts, debug, and all the details that I leave you to the episode 1. So once this core is actually verified, then given that as assumed, we can embed it in another system as this Core5 MCU, which will have then the Efpga memories and peripheral. And from that point on, what has to be tested is the whole system, not just the core. And we still have to define and discuss the strategy, but
will be different from what we've seen in episode 1, because it won't be IP centric, but system centric.
Tim, do you have anything you want to add to that?
Yeah, as David said, that the core has to be driven, because it's the primary thing coming out of Open Hardware Group, has to be driven to a very high level of quality. The Arnold 2 project with the CORE-V MCU SoC is more designed to be an evaluation platform of that core. So we don't expect to do the same high level verification of all of the peripherals. They're mostly there to let you do system use cases. So they need to function correctly. They don't need to carry out all the corner cases and that kind of stuff that you'd have to have in a commercial product.
Good. All right. So actually, let's talk about the SoC. We've had some questions around, is this going to be a commercial product, the Core-V MCU SoC, and the intent. So I'll talk about it for a second from an Open Hardware Group perspective, sort of build on what Tim just said, and then let you guys comment on the commercialization aspects of it. So the intent here is that not only are we focused heavily on quality with the verification test bench, but taking these open source artifacts right through a physical design flow, mapping it into a current technology node, in this case 22FDX, building what is a compelling product with the intent that this is a product that can be taken to volume production. We will not be producing a volume production device. We will be producing somewhere between, we as in the Open Hardware Group community ecosystem, somewhere between 1,000 and 10,000, just to give you an order of magnitude flavor, on eval boards. The only way you'll be able to get this from the Open Hardware Group ecosystem is on an eval board. And then any member or anyone, since the work that we're doing here is open source, to the extent of what we're building, anyone can then take that database and turn that into, this will be built on MPWs, so anyone can take that database, turn it into their own custom device, and replace any of the IP, peripheral IP that Tim mentioned, with whatever they would like to replace it with, or use it as is, and go to volume production. So that's how this will show up as a project within the Open Hardware Group ecosystem. And Brian and Tim, maybe you guys comment on commercialization aspects and what your motivation is there.
Yeah, I can cover that, Rick. So our motivation is twofold for this, as I said in the opening remarks. One is that we want to inspire other ideas and use cases for embedded FPGA tightly coupled with a RISC-V processor, and I think this is a great vehicle to do that. So that could, in the future, drive further business around our embedded FPGAs. This also gives us the ability to use the Core-V MCU as our next generation commercial product as a roadmap device. And as Rick said, not coming out of the Open Hardware Group, this would be something that would be coming from QuickLogic at that point, but it's basically sort of done and ready, and we can just do the production tape out and take it out ourselves with whatever minor modifications we want to do at that time.
Right. Okay. There was a question for ARC around Skywater and the Open PDK and so on, and how that relates, if that relates to this or whatnot. So Brian Wisk, you want to talk about maybe your interest in Skywater and that open source PDK that's been announced?
Yeah, I mean, it's a sort of customer manufacturer relationship. We have a custom temperature sensor there. I would say that how it relates to what we're doing is obviously, we're supporting any sort of open source initiatives, although we're not directly involved in what was mentioned in the question, as far as Google and Skywater and open sourcing S130 or open source PDKs. The company that brought us to Skywater, Linear ASIC, has done a lot of great work to that end. And Linear ASIC was who brought us to QuickLogic as well. So it's, sort of over time, I think hopefully there'll be a lot more people who are interested in pursuing this area of work, and then both commercially and academically, and just as a consortium, be developing things that actually can be used in a commercial setting on top of this stuff. So that's the connection there.
Great. So lots of questions about the embedded FPGA have sort of floated in here, and many related to what kind of applications have been run on this array. What size of array are we going to be putting in here in terms of LUTs or equivalent gate counts, that kind of whatever kind of metric you want to use. So Tim, maybe you can and Davide, maybe you guys can talk about the application performance capability of what we might be able to achieve with the Core-5 MCU SoC in the embedded FPGA in particular.
If Tim, I can start talking about the Arnold 1.0 version of this MCU. And the eFPGA we integrated in that MCU in the same technology was 32 times 32, so it's around 40K lookup tables. And we mapped inside from accelerators for the CPU, like binary neural network accelerators or accelerator for securities and for CRC and so forth. Or we also implemented custom peripherals, so to drive peripherals that have not a custom protocol or that require different kind of knowledge processing and stuff like that, or filters for the data coming from peripherals. And the frequency, of course, so for what concerns performance, the frequency changed depending on the actual hardware you mapped into the FPGA, and you can achieve more than 400 megahertz for a simple counter, as you can go for 100 megahertz if you start dealing with memories and computation from memories operand and so forth. So this would be the performance range. Power-wise, it's in the edge computing IoT domain, so it's always bounded to the milliwatt and below the 50 milliwatt or 100 milliwatt boundary. So in my cases, for the applications I've been running, we were talking about 6 to 10 milliwatt.
Yeah, and at QuickLogic, we've been looking at the visual wake word example that Google has in a TensorFlow algorithm, because TensorFlow is one of the very popular ways of doing artificial intelligence. And the way TensorFlow works is you have a bunch of operations or kernels, and in the visual wake word, they have two, convolution and depth-wise convolution that they use a lot. So we looked at pushing both of those into the FPGA as an accelerator. And what we found was that, yes, that's relatively easy to do. The system that Davide set up works very nicely for that. And it appears that we can get either 9 times the performance that we would get from the RISC core alone. So you get 9 times performance improvement, or you can get 6 times better power efficiency. So you can cut it either way. So I can get more performance or better power efficiency. And as David has said, the size is not enormous, but it's big enough to hold these kernels. And then the RISC core itself runs fast enough to feed them and keep up with it. So that's critical to the acceleration.
Cool. Come back sort of to verification. There's a couple more sort of questions theming around verification, which is not surprising because the biggest obstacle that the ecosystem see or commercial companies see around adopting this kind of open source IP is, you're going to go into your boss's office and bet your badge on an IP block that you downloaded from a GitHub repo from a university research lab, right? Probably not. So a couple of more questions around verification, which we're always happy to talk about. It's probably the most important project that we have underway within the Open Hardware Group. One of the questions is, when do we think we're going to replace the commercial tool flow with open source verification tools? And I would say not anytime soon, right? And the real question I think to ask, so a couple of things. I mean, I actually get this on the chin a little bit when I give talks in public forums around the fact that we're an open source organization, but we've got all these commercial, proprietary tools all over the place. And, my experience in developing open source ecosystems is they are successful if you have a clear path to commercialization. If this IP does not get adopted by large companies who figure out how to create a business model around it, it's still open source IP, obviously, but we need to drive commercial benefit. People won't participate just because it's fun. So driving commercial benefit and use of the open source IP is important. And the reality is there is no major chip company today that leverages open source tools in their known good, first pass golden tool chain environment. In fact, if you decide you're going to suggest that you're going to mess with the tool chain in a large merchant chip company, that's almost a fireable offense in some of these large companies. So we have nothing against the efforts going on with open source EDA tools. This is a tough nut to crack. It's, maybe the industry will get there. Maybe that's an area that, will eventually see widespread adoption, and different economic models will emerge in the CAD industry around that. But what we're trying to make sure happens is that the IP that we produce has high quality and can be adopted easily by the existing large volume production SoC guys. And to do that means that we need to stitch easily into their commercial tools. And so, I know it sounds like a little bit of perhaps a dichotomy or a departure from the open source ethos. But we believe pretty strongly that we're not going to try to boil the ocean with one match. We would like to be successful as an industry and be able to demonstrate some adoption of open source hardware-based IP, and that'll come, and then other things will come from that. But being able to demonstrate success and integration of open source IP will hopefully lower the barrier to entry for other activities around open source enablement and development. So the other question around RTL or around verification is, well, how do we measure success? What is done in the verification environment? And that's always a thorny question inside any semiconductor company. When is finished? How do you measure good quality RTL? And Tim, I see you smirking a little bit there, so I'll let you chime in on that one first. How do you know what is good RTL?
Well, I was just laughing because I remember something Vic Kalkani at ANSYS used to say, which is the only code that doesn't have bugs in it is obsolete code, meaning you stopped using it. So you're right, it's a thorny question. There'll always be issues in there. But I think this ties back to you using the commercial tools to do this, right? People will trust the commercial tools. So if you can show that by the commercial tool metrics that you have, good quality, people will believe that more than they believe open source tools, for instance. So you're back to the normal things that you would do as a commercial designer, right? What level do you hit?
Yeah, and in fact, that's exactly what we're trying to do, is replicate the experience that a large chip company would have if they were licensing, commercial IP from an IP vendor. There's a lot of work to do, and clearly established IP vendors have executed many test cases, and the IP for popular IP, it's been used widely. So that's a challenge similar to our BHAG challenge that we talked about earlier in the episode, but nonetheless, that's what we're trying to achieve. And for those of you that are watching and have a lot of interest in our verification approach, I encourage you to go to our GitHub repos and take a look at the Core5 Verif repo. That's the complete test bench, the stimulus, everything is open source. We have make files so that you can clone that environment, and we have make files so that you can build that environment with the simulator of your choice. So we're really trying to make it easy for folks to adopt this verification methodology. It's a step and compare based methodology where we compare the DUT result against a golden reference model from Empiris at the retire of every instruction, compare the program counter and CSRs and so on at the retire of every instruction. And in fact, as soon as we turned on step and compare in the test bench, we found a bunch of bugs both in the core. We found a bug in the RISC-V DV Google generator. We found bugs in test cases that had previously passed. So there was, there's been a lot of work to improving the quality and coverage that we're seeing in these cores. Okay, go ahead, Tim.
I have another comment on that, by the way. So, as a semiconductor company, we've acquired and used a lot of IP that's being verified by IP vendors. And much of that has had some kind of issue that we've struggled to understand. And usually issues you can work around if you can understand them. So one of the advantages of having an open source verification thing is you can look at it, see what it did, and make guesses as to what's failing in your design and come up with a workaround. And that's very hard with the commercial IP because all that stuff's opaque. You just know it didn't work. What do I do?
Yeah, and what's interesting too is that's a very good point, because each of the memory companies that are participating and helping with the verification work are bringing their own use cases to to the table in terms of wanting to see what kind of corner cases are being verified and how they're being verified with the particular application space that they're trying to cover. This core, the risky core, which we call CV32E4, has been taped out many, many times. It's in production now. And just, a bug in the way that I use the core might not even show up in a way that, say, Tim uses the core, as an example, depending on what the use case is and what the data set is that we're focused on. So that, the work that we're doing here does not in any way, shape, or form invalidate what's been done before. It just builds on it. And we believe we're building the most comprehensive and robust verification environment for these open source artifacts, and trying to really, really decrease that barrier to use and increase the confidence that end users can have in adopting these cores in high volume production SoCs. So let's drop the verification. By the way, we'll take a couple more questions and respect everyone's time and be done at the top of the hour. We still have quite a few questions in here and a number of people still watching us talk to each other. So we'll do that. There's a question here about the versatility and benefits of an embedded FPGA in an MCU. And does it suggest a rethinking of the design of domain-specific sensors that current MCUs are used in? And does that imply that we're going to need to have more mixed signal capability to support that? Well,
I can take that. I think the answer is we believe it does, right? Especially in the IoT space, because we think there's a couple things going on. One, with mass customization, it's hard to build one CPU that does everything. It's hard to predict the future. So having the eFPGA in there provides you the flexibility to adapt to future needs and change need for specific domains. And then on the mixed signal question, that's not really an eFPGA question, but my personal belief is, yes, in the IoT space, you're going to need a lot more mixed signal. And the reason is because the world's analog. All your transducers are analog, so eventually you have some analog signal that you got to convert to digital. And if you have a high volume thing like an accelerometer, people have put the digital interface on it, so that's fine. But in the mass customization space, you're going to be attaching to different transducers where people haven't spent the time and money to digitalize them. And you're going to need to have that in your device.
Right. So I think that's going to take us right maybe to the top of the hour. I want to throw another question in for Brian Wisk that's in here just around. It kind of repeats what we were talking about before, but this viewer might have missed that part of the episode. Why do we have a private equity investor hanging around with a bunch of open source hardware nerds?
Besides being one myself.
Yeah, but you've had the full throttle lot of it. You're okay now.
No, I think as I answered when we did this on the live chat, based on what Tim how he answered this, I think it's a really great question, the versatility benefits of an MCU, and does that suggest rethinking design? I think absolutely it does. How peripherals interact with the physical world, translating that into some sort of digital bit stream, and then how you apply some sort of classification algorithm and spit that back out is going to be an area of massive innovation. And I think it's the only way that we can, I actually think such a low level problem could expand in solving a lot of very high level domain problems for users, where like driver assisted vision system, like things that for everyone in the 21st century, they're just not even going to know how this works. How does this happen? So starting, going all the way down and saying, well, what's the limiting factor? What's the gate here that we have to improve the speed at which we can customize and really learn from the mistakes? I don't think a private closed book IP world can really survive that rate of acceleration. So that's the investment bet that we're making. And we're pretty strongly, we have some strong opinions about that as a firm.
Good, very
Could
good.
be wrong, but hopefully not.
Well, it's better to be firmly wrong than wrong in a wishy-washy way.
Yep.
So with that, we'll leave the final word then with you. And thanks to our panelists and speakers for participating in this episode, and to you viewers for watching. Mark your calendars for October 22nd, especially all you verification guys that had the questions today. Well, episode 5 on Thursday, October 22nd, will be focused specifically on the criteria for how we have communicated done. We'll be declaring our RTO freeze milestone, and there's a whole checklist and criteria for that. And we'll talk through that, and the panelists and speakers will be the contributors who participated in generating that verification test bench. So it should be an interesting discussion for everyone. So thanks for viewing today, and wherever your day is, I hope it's a good one. Thanks very much.
Thank you. Bye.
Thank you.